Yes, and give grades accordingly. Just assume that everybody did it right.
Oh, you never said anything about right. Okay. I feel like it's too early for this barrage of information, so you might want to go back and refer to the video for if you want to recollect any of this. But do keep in mind that this might take some time, the experiments. So you might want to start early. That said, the SVM/ensemble homework is actually kind of among the easier homeworks in the following sense. If you have implemented perceptron, SVMs are easy because it's literally just a few characters change in your old code. If your perceptron was right, with high probability your SVM will be right. Your decision tree is also something that you have probably implemented or come familiar with before. So this is really asking you to use these building blocks that you have and glue them together into something big. Okay? So on that, in that sense, it's kind of easier, but on the other hand, it's going to take some time, and there are 2 data sets, you have to do more experiments and all that, and then you have to somehow play around with this splitting rule. How do you bucket the features, and that might take some getting used to. So anyway, get started, or if you haven't started, get started. If you've started, good job. All right. Any questions at all? So if not, I'm going to continue where we left off. We're almost done with kernels. I just want to remind you about a couple of things with kernels and then move on.
Well, I do have a question.
Okay.
When do you think we'll hear or get feedback from our
Projects? I'll try to do that as soon as possible because there's roughly a month left. So I would like to get back to you hopefully in a week if possible. Alright. Kernels. We were talking about kernels in the last lecture. I just want to summarize what we saw because we covered a lot of slightly different ideas and I just want to put them all on one slide. The hope here is that we can somehow use to build nonlinear classifiers using the technology that we know, using the idea of support vector machines. And one way of doing this is to take your features, whatever feature space you have, and blow it up to a different feature space, where the features themselves encode nonlinearities. And this should not be a total shock to you because we've been seeing this for a while now. And at the end of the day, once you blow up the features into a nonlinear, using a nonlinear transformation, you get a nonlinear classifier. It so happens that for support vector machines, whether you do this or not, it just so happens that for support vector machines, the final weight vector that you get at the end of optimization is a linear combination of the inputs. Which means when you take a dot product between the weight vector and the new example at prediction time, it ends up being a sum of dot products between things that are instances. Now, instances could either lie in the original feature space or in the blown up feature space. So really, the fundamental operation that's needed to make the support vector machine work is these dot products between examples. And so you can either compute the dot product in the examples between the examples by actually doing the feature expansion, or you can come up with this cool computational trick, one for each kind of a dot product. It's called the kernel trick, and we saw examples of this. The kernel trick is a computational tool, a device that can compute dot products in higher dimensional spaces efficiently. And we saw examples of various kinds of kernels. More generally, a kernel function or a kernel is simply a function that takes 2 vectors and produces a number. This number, it cannot be any function. This number has to be a dot product in some space. Okay? Which means that not all functions that take 2 vectors and produce a number are kernel functions. They have to correspond to a dot product, and that was the gist of the Mercer's theorem that we saw in the last lecture. Any questions about this stuff? Yes?
So are we saying, like, maybe I know I want a feature expansion, but I don't necessarily even have to care what it's going to end up being. I can just pick some kernels and try them see if the kernel works without thinking about the expansion?
Basically, every kernel corresponds to a feature expansion. Every kernel corresponds to a feature expansion. So instead of trying out expansions, you're trying out kernels. It's the same design choice, except once you are creating a kernel, it might correspond to a kernel trick, which might give you this computational advantage.
Okay.
In some sense, the kernel trick is just a computational trick. It doesn't change anything in the map. So, and we saw multiple ways of constructing kernels in the last lecture. Yes?
So, if you ran the test and it is a valid kernel, does the kernel trick necessarily work for a valid kernel?
What does that mean?
I mean, can you apply this shorthand to any valid kernel?
So, I don't get that question. Can you expand on this? Because I feel like there's something that's missing here. So, let's pretend that we have a function.
Yeah.
Okay, let's say that we have a function. Let's not call it k. Let's call it some function f. It's a function that takes two vectors and produces a number. I don't know if it's a valid kernel because it's just a function. For it to be a kernel, it has to satisfy that property. So I cannot use an arbitrary function. But if I know that it satisfies the property, the fact that the Mercer's theorem, if I know that it satisfies Mercer's theorem, then I know that there exists some space which some feature transformation.
Okay.
Does that make sense?
Yeah, that makes sense.
I don't know if that answered your question because I didn't understand your question.
No, it does.
Okay. Okay, there's another question.
Given an arbitrary expanded feature space, can you find a kernel?
Sorry,
Given an arbitrary expansion, can you find a kernel?
well, the dot product of that expansion is the kernel, right? If you have given me the expansion, I can define the kernel in the following way. I take the two vectors, let's call them x and x prime. I take the two vectors, convert x to that new space, convert x prime to the new space, take the dot product, I get a kernel. It's not it may not be efficient, but it's still a kernel because it's a dot product. Right? Yes.
Do we have to expand to a higher dimension feature space to call it a
it's
kernel?
just a different space. It's
Okay.
just a different vector space. The dimensionality doesn't really matter here.
Okay.
Yeah. Other questions? So we also saw how to construct kernels. If I have a kernel function k1, k2 or something, if I have a kernel function k, then we can construct new kernels. If I know that k is a kernel, then c times k is a kernel. If I know that k is a kernel, then multiplying it by some function of both the inputs is a kernel. If I know that k is a kernel, then a polynomial. In fact, I think your homework asks you to prove that statement. If I know that k is a kernel, then e power k is a kernel. Yes?
How can we be sure the program is linear for in the new space?
Sorry, how can we be sure what?
How can we be sure the program in the new space is linear for?
Is
linear.
Is linear. Well, if I expand it out, any polynomial is linear in a high dimensional space. So, if I can tell, for example, if you have x1 plus x2 square plus sine x1, it's not linear, right? But I can argue that it's linear in the following space: x1 square transpose 1, 1, 1. Now I'm going to call each element here, this is z1, z2, z3, transpose. Now x1 is the same as z1, x2 square is z2, and sine x. In the new space, in the space of the z's, it's linear. So I can rename these monomials or nonlinear terms, just call them new names, and in the new space it's linear. So I can expand out any function is linear in a high enough dimensional if I am allowed to have arbitrarily complex dimensionality. Right? Alright, so there are ways of constructing kernels. So I want to end this whole section with an example of a kernel trick. And I don't want to take too long on this, but this is kind of cool, and I was planning to skip it and make you read it, but I think it's entertaining enough that it's worth showing off. So let's say, let's pretend that our examples are all Boolean vectors, and the blown up feature space is the space of all possible conjunctions. If I have n variables, I have 3 power n conjunctions, right? The blown up feature space is just basically this 3 power n dimensional vector of every possible conjunction. So that is this phi here. And I'm going to define the kernel K as the dot product of these two, of this blown up feature space. It turns out that this particular kernel can be computed way more efficiently without ever converting this thing into the feature space by counting how many bits are identical in x and z, and 2 power that number is the value of this k. So let me give you an example. Suppose you have 3-dimensional points, n equals 3, and let's say you have x equals 0, 0, 1 and z equals, is this visible all the way at the end? The font is pretty small. Okay, so x is 0, 0, 1, z is, what is that, 0, 1, 1. Now you have conjunctions. So just to give you an example of what I mean by the blown up feature space, let's actually explicitly blow up the example x. So phi of x looks like this. There is one feature which is always true, that corresponds to the empty conjunction. Then there is just the x, this, let's call this x1, x2 and x3. x1, x2 and x3. x1, x2, x3. And then all possible, and I want all negations also. So I want not x1, not x2, not x3. And then I want x1 and x2, x1 and not x2, all the way down. All the way down to not x1 and not x2 and not x3. That's your feature space. If the actual instantiation of this feature, the feature expansion for this particular x1, x2, x3 looks like x1, the 1 is always 1, x1, x2, x3, they are 0, 0, 1. But then I also have the negation. So that is 1, 1 and 0. So this corresponds, this block corresponds to this block here. And then x1 and x2, they are both 0. x1 and not x2 is 0. Not x1 and x2 is 0. And then not x1 and not x2 corresponds to 1. This corresponds to 1, right? And so on. I can keep growing this all the way down. There will be 3 power 3. There are 27 features here of every possible combination of x1 and x2 with possible negations. Is the blown up feature space clear? Does that make sense? Okay. So now, before I erase this, are there questions about just this part so far? This aspect, this part of the example. Okay. In that case, so I can technically take x, convert it to this space phi, take z, convert it to the space phi, and I can compute the dot product of these two things. What I'm claiming here is that this is identical to counting how many of them are the same. So you have x is 0, 0, 1, z is 0, 1, 1. These two are the same, this is not the same, and these two are the same. Right? The value of the dot product, I claim, in this case is 2 power 2, is 4. You don't need to do that expansion. You can just count how many bits are identical in x and z and take the 2 power that, and that is the value of the dot product without actually doing the expansion. Isn't that cool or what? Now doing the expansion takes you, like, I can't fit it on the board, but I can calculate the value of the dot product right there. So it's an entertaining exercise in trying to prove this. So let me give you a hint. So what you need to do is to identify which, when you take conjunctions of variables, think about what happens to the conjunction. Which conjunction survives? So let's consider x. First of all, let's consider the dot product. What does the dot product mean? It's the product of all possible pairs of the blown up vectors and add them up. Every element in the blown up vector, in the transformed vector, is a 0 or a 1. An element will survive only if both of them are 1. right? Only those things where both of them are 1 will contribute to the dot product. So let's ask ourselves, which of the conjunctions will survive? So for x1, let's consider one feature, phi I of x is, let's say, not x1 and not x2. That is some ith feature. Phi I of z is not z1 and not z2. The first one, in this case, the corresponding feature here is not for 0, x1 and x2 are 0, 0. So not 0 and not 0, which is 1. Right? In the second case, it is not 0 and not 1, which is 0. So this product, the product of these two things will not survive. So let's ask ourselves, which of these things will survive? The only ones that will survive are where both these entries are identical. Right? The only ones that will survive are the ones where the common elements here. So, for example, not x1 and x3 is 1, not z1 and z3 is also 1. So that product will survive because the product of these two things will contribute to the sum here. So the only ones that will survive are when the variables that are here have the same value in the conjunction, in this case. Both of them are, one of them is 0, the other one is 1, you add the correct polarity and that's how these things survive. Does this intuition make sense? I mean, this is kind of a way to a formal proof. Everything I'm saying here is not a formal proof by itself. So, everything outside the set will disappear, and yes, you have a question.
I think it's a fundamental question. Like if somebody asks me what is the kernel in this example, what should I say? Is it a P or
K.
is it to the power of same?
No, K is the kernel. The kernel is just a function. I mean, it doesn't matter how you come. I want you to differentiate between a function and how you compute it. This is the difference between, say, a function and a method. A function is a mathematical object. It takes two vectors and produces a number. How you compute it is, you can compute this value of the function in two ways, either by expanding and adding and all that, or by just 2 power n. I can compute it in two different ways, but the function is just the same. It's just the same function. So the kernel is the function.
Is the conjunction or the answer?
No, the expanded feature space is the set of all conjunctions. The kernel is defined as K. K defined in this whole, the whole thing here defines the function. In fact, I could say that even without this part here, I can call it a kernel. Yes?
What about the conjunction x1 and x2, like just pick phi sub I as x1 and x2,
Okay.
and z1 and z2, and then x1 and z1 are both 0, and doesn't it not matter what x2 and z2 are? Those
No,
things-
x1 and x2 are both 0.
So then the whole conjunction will be 0.
Is 0, right? And what is that x?
So z1 and z2.
Yeah, z1 and z2 is 0, so the product is 0.
But isn't x2 and z2 different? You were
Yeah.
arguing that all the input variables had to be the same.
No. So this is, yeah, of course, these two are 0. So when you take the product of these, it disappears. On the other hand, what I mean by same is, so you have, let's keep this block here. This is 0, 0, 1, and this is x, and z is, what was that?
0, 1.
0, 1, 1. Instead of thinking of it that way, think of it, let's write down all the surviving conjunctions. All this, okay? So the conjunction that's just not, so not x1 survives. Not x1 is equal to 1, not z1 is equal to 1. So, so this one will contribute to the dot product.
So So the only ones that end up being ones were the ones where they do.
Yes. Similarly, x3 is 1 and z3 is 1. So this will contribute to the dot product, the product of those things. The only things that will eventually contribute to the dot product are combinations of that, right? So not x1 and x3 is 1, not z1 and z3 is 1. So this will contribute to the dot product. And then the empty set. So there is one conjunction whose size is 0, that's always equal to true. So true equals 1, true equals 1, this will contribute to the dot product. All other terms will be 0. Either one of these elements in the vectors will be 0. There are only 4 things that will contribute to the dot product. That's why the dot product is 4. Does that make sense? So to answer, go back to your question, what is the kernel here? The kernel here is the function that takes 2 vectors and computes the dot product in this way or in that way. But actually the function, the mathematical object is the kernel. Was there another question somewhere here?
Oh,
Yes.
so I was wondering, I guess, is it ever, like, I guess, impossible to either, I guess, compute or define, like, phi itself, but you can, like, find a kernel for something, but, like, you can't actually determine what that is, but you can use the kernel?
Yeah, there are definitely ways of doing that. In fact, there are some very cool ways of doing that, and I don't want, let me just say yes, and if you're more interested, you can talk to me later. There are some interesting ways where you can write down the kernel, but you don't know how to compute. It's not clear what the actual lifting map is. Alright, so I'm going to end this with a couple of exercises. I want you to convince yourself that this example is actually correct by taking a different x and z, let's say 4 dimensions. Let's take these 2 examples. Take the effort of writing down the phi, the feature transformation for x and z according to this method. It's an 81 dimensional vector. You will hate yourself, but trust me, it will do you good. You'll just see the intuition by doing it, and you compute the value. And then you'll also, just by doing that, you'll automatically notice that the kernel value is 2 power same. In this case, it's 2. For these 2 things, how many bits are same? There is 1, 1 and 0. The first 3 bits are identical. The dot product here, without even computing the 81 dimensional vector, is 8. The dot product is 8. I don't care about the 81 dimensional expansion. But I want you to convince yourself that's correct.
This only works with 3 to the n conjunction.
Yes, that's your second exercise. The second exercise is I want you to develop another kernel. When I say develop, I mean come up with a kernel trick just like this, the computational trick, for a different kernel where instead of considering all possible conjunctions, consider the feature expansion of only conjunctions with size 3. So you will not consider you will not consider, say, x1 and x2. You will consider x1 and x2 and x3. This is not allowed, this is allowed. Again, try to invent a kernel trick for this. It will really give you an idea of the computational gains that can be made. And I strongly encourage you to do this because this will kind of gel the idea of, this will kind of solidify the idea of what is a kernel and what's the difference between a kernel and a kernel trick. Alright, so let me start wrapping this up. Just to remind you what all this is about. We are computing dot products. End of the day, we still want to compute dot products between weights and features. The kernel trick is a computational shortcut that lets you compute these dot products in high dimensional spaces efficiently. And it turns out, even though in the literature you'll often see kernels associated with support vector machines, this method, this idea of computing dot products efficiently is a much more powerful one. In fact, it's somewhat easy to create an algorithm called the kernel perceptron, which uses the kernel trick and applies it to the perceptron algorithm. If you want, we can talk about that later or not, but it's actually fairly easy to even implement the kernel perceptron. You just have to pay a big memory price. The most important thing that you should take away from this, apart from all of this, is the fact that even though you might be able to compute the dot product efficiently without leaving the ambient space, without going to that high dimensional space, you should remember that this classifier that you might train using this using this high dimensional transformation is still a classifier in the high dimensional space. If you are computing a dot product in this 81 dimensional space, then all these VC dimension or learning theory bounds and everything that use the dimensionality, what's the dimensionality that matters? It's the higher dimensional thing, because that is the space in which your instances are now operating. For example, let's say you start off with a 100-dimensional vector and you train something like an SVM, and you get some, let's call that option 1. What's the VC dimension of a 100-dimensional vector for a linear classifier in 100 dimensions? 101. Now let's say I take the same example, but let's say just to make my life easier, I do an explicit feature transformation. I go from 100 dimensions to 100 square, 10,000 dimensions. But using some computational tricks, I'm able to get away by doing only operations in the 100-dimensional space. Doesn't matter how. It might seem like you're doing it computationally, this is easy, but the ambient space that in which your classifier operates is still 10,000. So the VC dimension there is actually 10,001. You are operating with classifiers of a much higher capacity. So your classifiers might end up overfitting your data. An extreme example of this is the RBF kernel. The RBF kernel or the Gaussian kernel, the blown up feature, the transform feature space for the RBF kernel is an infinite dimensional space. So it can overfit any training set. So if you see a paper where it seems like an RBF kernel gets the best accuracy, you must ask yourself, how have they regularized? Is there any overfitting going on? Because it might end up overfit with high probability. So you have to be careful of using these bigger and bigger kernels. That's the lesson here. Okay? Yes?
Is there a way to count the number of support vectors and say this is overfitting? Because as you go to higher dimensional space, you could end up with all the data points.
It's hard to say that because it's hard to say whether you have noise in your data or if the concept itself is difficult to, if the concept is difficult to learn or if you're overfitting. There's no easy answer there.
There's no metric that says,
no.
Okay.
Sadly no. But, this is a good segue into the next lecture, which talks about a couple of important points. In particular, really, there are only two things that I want to talk about in this lecture, and hopefully this is going to be a small lecture. We'll finish.
Another question.
Yes.
Did we already cover how to use kernels in SVM?
No, we did not.
Okay, thanks.
I will not talk about that because in order to actually write a learning algorithm with kernels in SVM, you need to transform your problem into the dual problem. Remember I was talking about the duals? You need to transform your problem into the dual, and your optimization has to proceed in the dual. So the learning algorithm in that case becomes way more messy that I cannot actually do it in one slide or in a class. But it's actually, it's fairly easy if you understand the optimization part of that. So there I have pointed some, I added some references in the SVM lecture page. You should check that out. It's easy and methodical, but very messy. It takes like a fair amount of calculus and keeping track of a lot of variables to make it work. Yes?
So in general, does someone that's trying to learn a certain data set just try different kernels? Like, I have 12 favorite kernels that I want to try. And
yes, you can do that. But then you have to do cross-validation to decide which kernel works. Right? So the libsvm package, for example, is designed to work with, is designed to let you use polynomial and RBF kernels easily, for example. A whole area of research is called kernel learning. transform the problem of learning what is a good kernel, of figuring out what's a good kernel into a learning problem. And not surprisingly, it's not easy. You run into a lot of issues with scaling, and it has never, it's mathematically beautiful, but it's never been convincingly proved to work because of these computational issues. It's an active area of research. Alright, so let me move to the next lecture, and hopefully I'll be able to get done with this entire lecture today. It's this idea about loss minimization. I'm going to talk about a very broad strategy for creating learning algorithms by writing learning down as an optimization problem, and then we'll get to the other stuff later. So the setup for learning as loss minimization is exactly the same as before. You have examples that are drawn from a fixed distribution, these are x's, and then there is this hidden function f that we don't know, it's an oracle classifier, and it labels all these examples. And our goal is to find a hypothesis that seems to mimic this f. And in the ideal situation, what you do is you write down a function L. L is called the loss function. L is the loss, or the penalty that your hypothesis suffers if it makes a mistake on, in general, L, you can think of L as the loss penalty paid by a classifier on a particular example. And one way of defining learning is to pick some function h, to pick the hypothesis h, that minimizes expected loss. Expected according to what? Expected according to the distribution of examples. The expectation is according to the distribution of examples. Does that make sense? So I define a penalty, I define a cost for making a mistake, and you want to find a classifier that has the least penalty. Notice that this is very abstract. I haven't told you what the loss function is. But there's a bigger problem, the fact that the distribution is unknown. So which means we cannot really compute this expectation. And the way to get around that is to use this training set that we have. We want to compute the expected value of the loss. Instead, we can calculate the empirical average, the empirical loss of the training set, which is just the sum of all the losses divided by the number of examples. So instead of minimizing the expected loss, we minimize the empirical loss. Questions so far? And I want you to think about whether this makes sense more than anything else, whether this seems like a sound strategy. This will overfit, yes, and that's definitely a problem. We'll come to that in maybe a minute.
Is this something similar to like the margin perceptron?
This is more close to the SVM actually. Why did you say that though?
Well, because you're saying now if it's beyond this threshold of margin, then I'm going to cut it off.
It's not exactly that way. This is batch learning. It's not looking at a particular example. It's computing expected loss or the average loss. And for example, it's possible that on a particular instance, on one particular x, f of x pair, this classifier is terrible. It suffers a massive loss. But on all the others, it's perfect.
So
in average, it might get even
across the data set entire.
Yes. Ideally, we want across the entire instance space. But we can't access that. Instead, we use the data set as a surrogate. Okay, so you want to minimize empirical loss on the training set, and you raised a question, which is there's a problem here. If I minimize empirical loss on the training set, the best classifier is the one that gets zero loss on the training set. If I forget how we find the classifier, but the best classifier is one that gets zero loss on the training set. And getting zero loss on the training set is not the greatest idea because of overfitting. Right? So if you get zero loss on the training set, it's possible that your classifier is overfitting. So we need to somehow augment this strategy by penalizing classifiers that overfit. In other words, more interestingly, it's you want to bias your classifier, your learning algorithm. The learning algorithm is whatever algorithm does this minimization. We don't care about it at this point. But we want to penalize the learner towards simpler classifiers, simpler hypotheses. because more complex hypotheses tend to overfit. Bigger trees tend to overfit, smaller trees tend to not overfit. So you want to somehow bias your learner towards these smaller hypotheses. This is also called regularization. The idea of kind of guiding your classifier towards simpler hypothesis is called regularization. Yes.
Was that what you were talking about when you were talking about regularizing the RBF?
Yes, that's exactly right.
Because I didn't recognize that term.
That's exactly right.
So you don't want to have too many Gaussians, just like.
You don't want to have too many parameters, or somehow you want to regularize.
Okay.
But in an abstract way, you need to somehow penalize complexity.
Okay.
But let's say we have this regularizer is a function that penalizes complexity. What does it mean to penalize complexity? We want to somehow fit it into this minimization framework. The way we can do it is to add two terms to the minimizer. So this is the loss term, the average loss. It's not just enough to minimize the average loss. We want to minimize the average loss plus a penalty term. The penalty term only says, I like the simpler hypotheses here. It's a function that takes hypotheses and produces a number. This number gets larger if your function is more complex, for example. And now the learning strategy is not just minimizing loss, but minimizing the regularized loss. The regularized loss is just the sum of loss plus some regularizer term. Make sense? So far so good? We've already seen this actually. We've already seen this because we've seen an example of a regularizer. One example of a regularizer that we saw, and probably the most popular regularizer that's out there, is this dot product of the weights. For support vector machines, how did we come upon this dot product of the weights? We said the classifier, so let's kind of recollect the argument. The VC dimension of a linear classifier depends on the margin. If the margin is bigger, the VC dimension is smaller. So the strategy is to find, so VC dimension, by the way, is a measure of complexity. So if the margin is bigger, VC dimension is smaller, which means bigger margins is somehow inverse of, so complex linear classifiers have smaller margins. We also saw that if the dot product of the weights is bigger, then the margin is smaller. So let me write this down. So larger margin implies smaller VC implies simpler. But also larger margin implies smaller W transpose W. So smaller W transpose W implies simpler classifiers. So W transpose W is a regularizer. It penalizes linear classifiers that have higher complexity. And that's why we have a regularizer term for linear classifiers. Yes?
So why does a larger margin imply a smaller VC dimension?
This was the theorem from Wapnick that we saw maybe a few weeks back. There was a theorem that had the margin, the VC dimension of classifiers with a certain margin is inversely proportional to the margin square. Yes, this is Wapnick. Okay? So we've already seen the idea of regularizer, we just haven't called it that. Alright, so that's the regularizer, but now let's think about what is a loss function.
So,
Yeah.
So if we blow up the feature space, getting a higher VC, because that means a higher VC dimension, and we can achieve a higher margin by doing that, right?
No, the VC dimension is also dependent on the dimensionality.
Ah, right.
So that will also give us trouble.
Right.
Yes. So that's pretty much it about the regularizer for now. So the regularizer is just a function that penalizes complexity, and we don't know which classifier to pick. We want to trade off these two terms. We want to somehow have a complex enough classifier that achieves small loss. So we want to minimize complexity and loss. And the way to do that is to minimize the sum of those two things. Oh, I think my pen has stopped working. Yeah. The way to do that is to minimize the sum of those two things. The first term says I want less complex hypothesis. The second one says I want smaller loss. Okay, that's enough about the regularizer for now. Tell me let's talk about the loss function. The loss function penalizes mistakes. We want to minimize average mistakes, if you want. What is the perfect loss function? No, what's the perfect loss function? I need a function that takes a prediction and a gold label, the true label, and says, it gives 1, says true if there's a mistake, and false if there's not a mistake. Yes?
Oh, I was just throwing something out there that you just have an infinite penalty for any mistake.
You can have infinite penalty for a mistake and 0 penalty if it's correct. But that seems too harsh, right? I mean, that will flounder in the face of noise. So instead, let's have a constant penalty for a mistake, some big number, and a 0 penalty for no mistakes. What's a good constant? 1. You can always scale things if necessary. So that's called the 0-1 loss. The 0-1 loss simply says, if the true label is not equal to the predicted label, then the penalty is 1. If the true label is equal to the predicted label, then the penalty is 0. Notice that the average of the 0-1 loss is actually the error of the classifier. Right? You add up all the mistakes and divide by the number of examples. So that if you care about accuracy or if you care about minimizing error, then the perfect thing to minimize is the 0-1 loss, because it's exactly the thing that you're measuring. For linear classifiers, we know that the prediction y prime is simply the sign of W transpose X. And we've already seen this, that a mistake is simply if y times W transpose X is less than 0. So for a linear classifier, the 0-1 loss can be equivalently written as, if you have an example X and the true label Y, you take the dot product of the example with the weight vector, and if the product of the W transpose X and the true label Y is negative, that means you made a mistake. If you made a mistake, the loss is 1. Otherwise, the loss is 0. This is the 0-1 loss for linear threshold units. Yes?
Maybe you're getting this. I guess I don't understand why that would be intractable. You just iterate over your data and see how many mistakes you have.
That's for one. That's true. That's for one classifier. What I care about is searching over the space of every possible linear threshold unit, iterate over the example for each one of them, and find the linear weight vector that has the minimum loss. Right? I want to find the classifier minimize over W plus C times this quantity here. But I want to find minimize over W. Computing the loss is easy. You just iterate over the training set and compute the error. But finding the weights that has the smallest possible loss is NP hard.
You could just use gradient descent on your loss function?
This function does not have a gradient. This function is not differentiable. That's my next slide. That's this function here, this step function. If y times, this is y times W transpose X. If y times W transpose X is positive, then the penalty is 0. If y times W transpose X is negative, the penalty is 1. That's the step function here. And this is not differentiable.
But I mean, for example, like stochastic gradient descent doesn't depend on having a function. You just perturb your W in every direction.
This is not even a continuous function. This red line here should not exist. This is not even continuous. At 0, this discontinuous.
Well, you don't need it to be continuous because you're not actually taking the derivative.
And the derivative on this side is 0. And the derivative on this side is also 0.
Okay.
So this is a nuisance.
Okay.
And but this is a good, the discussion that you just provoked is good because it's kind of illustrative of the difficulties that you have with this loss function. So what we want to do is minimize the 0-1 loss. Actually, we want to minimize the regularized 0-1 loss. Unfortunately, the 0-1 loss is not continuous, it's not differentiable, it has all these annoyances from the optimization point of view. It's NP hard to find it's intractable. So instead of that, we invent surrogates, and we've already seen a surrogate. We've seen this surrogate called the hinge loss. Remember the hinge loss? The hinge loss is this function that's maximum of 0, 1 minus yw transpose x. This is, I'm going to call this L hinge. Now let's examine the hinge loss as in connection with the 0-1 loss. So remember, everything on this side of the axis, when yw transpose x is positive, is not a mistake. Everything on this side is a mistake. The 0-1 loss says if you make a mistake, you pay a penalty of 1. If you don't make a mistake, you don't pay a penalty. The hinge loss, on the other hand, says mistakes get an increasing penalty as you go farther and farther away on the wrong side of the hyperplane. That's on this side. Even if you are on the right side on the correct side of the hyperplane, if you are very close to the margin, you still pay a little bit of penalty, because as you go up, that's the penalty you're paying, that's the loss. So the only way not to get a penalty is to find a weight vector so that all points are outside the margin. So the hinge loss says it's not enough if you just it's not enough to not make a mistake. Even if you are correct, but inside the margin, there's a penalty to be paid. And this is a convex surrogate. By the way, the other problem with the 0-1 loss is it's not convex. This is a convex surrogate for which we can calculate subgradients and invent the subgradient descent algorithm. Make sense? Questions about the hinge loss?
This is much more sensitive to noise, right? Because even if there is one outlier that's noise that's going to...
You pay the loss. You pay the loss. You can. The idea is that you eat the loss and find the weight vector. If there is no other way, then that's the minimum, right? That's the minimum expected. The loss that the function that minimizes the loss is the one that you pick. But you're right. If there's one example on that has the noise, then you pay some penalty. But it's the minimum. You search for the minimum penalty. Make sense?
Yeah, but in certain cases it will be like horrible, right? Like, say, or the noise is like pretty fast.
That's right. In some cases it will be horrible. So, and such is life. We are given a data set where there is so much noise. For example, the data sets that you guys are playing with right now. We have to pay the loss penalty. There's no other way. And this kind of, notice that the loss here over specifies is always on top of the 0-1 loss. It's always more than the 0-1 loss, so it's more conservative in some sense.
Does it have to be a 1 minus? Is it just arbitrary? Or?
The 1?
Yeah.
This 1 is this 1 here.
Yeah.
And that's just saying this is the margin I want. I want this margin.
So does the margin have to be 1?
It doesn't matter. You can always scale it up. Let's say I put 2 minus, then I can divide everything by 2. I get W divided by 2. So the weight vector eats it up. Right? Because I can put, say, I make it max 0, 2 minus y w transpose x. I'll say this is the same as twice 1 minus. And w by 2, let's call it w prime. And that will be the one that it learns. Yes?
So I guess with the pathological case for kind of the hinge loss function would be is if you have like some point that it's strong, like should strongly classify ideally as like positive or something, but you end up like just its noise and it ends up being classified as negative, so it ends up with a really large.
It ends up really far away.
Even though it's just noise.
And if that happens, then the weight vector will try to compensate it by, the optimizer might end up trying to compensate for it by rotating the weights so that it pushes that point closer to this side. And it tries to find a sweet spot so that between that example and the rest of the data set.
But then maybe like the actual, the 0-1 loss might say, well, no, it's just no, just ignore it, because it's not that.
But we don't know, right? We only have the data set to, we only have the data set and we only have polynomial time to find a classifier. So this is one of the surrogates that we can use. But this is not the only surrogate we can use. There are others, and I'll come to that in a minute. So here's another interpretation of support vector machines. Support vector machines are a regularized loss minimizing machine. It's a linear classifier that's combined with regularization and that tries to minimize loss, but we can't minimize 0-1 loss. Instead, we minimize what is called the hinge loss. So support vector machines are classifiers that are linear classifiers that are trained by minimizing regularized hinge loss. It falls under this broader umbrella of learning algorithms that minimize empirical loss. This is an idea, this is a fundamental learning, machine learning idea called empirical risk minimization. Loss is also called risk. We try to minimize empirical loss, and support vector machines are an instance of that. Okay? But there are, and the way to think about this is, now we can actually analyze the SVM objective function from this perspective. The SVM objective has two terms. There's a regularization term, the W transpose W. The regularization term says, I want to maximize the margin, I want to minimize the norm. And why does it do that? It imposes this preference over simpler hypothesis spaces. It turns out this is just one way of writing down a regularizer. There's a whole cottage industry devoted to inventing regularizers for linear classifiers. We've just seen one of them. That's the first term. And there's the other term, that's the hinge loss. That's the empirical loss, the average or the empirical loss on the training set. Support vector machines uses the hinge loss. It penalizes weight vectors that makes mistakes and it penalizes them according to the hinge loss function. Again, variants of this exist. It turns out you can replace this part with other loss functions also. You can replace this part with other regularizers and you get different classifiers. For example, logistic regression. Some of you may have seen it. We are getting to logistic regression soon. Logistic regression also falls in the same umbrella. It has the same regularizer. It has something called the logistic loss. The perceptron algorithm, the batch perceptron algorithm, falls in the same family. It doesn't have a regularizer. It has something called the perceptron loss. Turns out AdaBoost also falls in the same family. AdaBoost minimizes something called the exponential loss. So the idea of empirical risk minimization is a very, very broad family that seems to cover a lot of learning algorithms that exist out there. And there is this hyperparameter C that trades off between these two terms. One way to interpret this is if this becomes very small, you will overfit. If this becomes very small, you will underfit. The C is a hyperparameter that trades off between overfitting and underfitting, between extreme expressiveness and very poor expressiveness. Because if the VC dimension is very low, you can't really express anything. And we don't know what's a good value of C, that's why we use cross-validation. Now, notice that first of all, I want to repeat or maybe state that everything that I have said so far today is not new. It's just a reorganization of the ideas that we've already seen. We have seen support vector machines. We have seen the idea of this, the margin being maximized by this dot product. It just so happens that this idea fits under a broader framework. And I'm just renaming all the things that we've already seen to kind of introduce the broader framework. So there are many loss functions. The perceptron loss is exactly the same as the SVM loss without the margin. The hinge loss has a margin, the perceptron loss does not have a margin. As an exercise, what you should do is plug in the perceptron loss into this sort of a framework here, get rid of the regularizer, derive the stochastic subgradient descent for that loss function, and convince yourself that stochastic subgradient descent for that loss function is identical, it's exactly the same as the perceptron algorithm we saw. It should not be hard, it will force you to kind of confront whether you understand stochastic gradient descent or not. AdaBoost minimizes this other kind of a loss called exponential loss. Logistic regression is a different kind of loss. We will actually, in a later class, we will derive the loss function for logistic regression by starting off with a completely different worldview, by starting off with the probabilistic perspective on learning, and it turns out it also fits neatly into this framework. If you like pictures, here are the different loss functions. This is the 0-1 loss is what we want to minimize, but we can't, and so we invent surrogates. One of them is the hinge loss. The hinge loss is what we saw before. The perceptron loss is exactly the same as the purple line is very similar to the blue line, except it's shifted. The perceptron does not have the idea of a margin. The exponential loss, AdaBoost minimizes what's called exponential loss. It's extremely conservative. It tries to, it penalizes mistakes quite heavily, which is an intuition for why AdaBoost has this property of overfitting a training set. The logistic loss we'll get to that later. I just wanted to put this on the same picture. Questions so far? There are many machine learning classes out there which start off with this idea of empirical risk minimization as the fundamental idea of machine learning and try to introduce all algorithms inside this framework. I'm choosing to do the opposite because I feel this is kind of a higher level idea. Yes?
Is there any benefit other than making math easier to having the loss function be smooth?
Is there? Actually, I don't know. It's almost a question of what code you have lying around. Basically, it comes down to that. There are some philosophical changes. Logistic regression gives you a classifier whose score can be interpreted as a probability. From first principles, we derive this logistic loss using a probabilistic way of thinking about things. Support vector machines does not give you good probabilities. But so it depends on whether you care about those kinds of things. But yeah, so if you ask me to choose between SVM and logistic regression for binary classifiers, I would say I'll use whichever one I have the code for. They tend to work roughly the same.
Okay.
So the other important thing to note here is I'm presenting everything here with respect to linear classifiers. At some point, I was thinking we'll do it in the next lecture, but I've decided I'm going to move the neural networks lecture to the end. When we come to neural networks, we'll see exactly the same idea works. It just so happens that the function that the hypothesis space, this h here inside the loss, is way more complex. It's not some linear function, it's a crazy non-linear function. But the same fundamental idea still applies. All you have to do is write down a loss function and then take partial derivatives, and the whole story just follows. So stochastic gradient descent is a recipe for building learning algorithms. I write down a loss function, I take the gradient, and I create learning algorithms. And backpropagation. How many people have heard of the word backpropagation? A non-trivial number. Backpropagation is a computational strategy that lets you calculate gradients easily. It's just a way in which you can do. Basically, it's a way of doing calculus. It's a way in which there's automated symbolic calculus. That's pretty much what backpropagation is. It falls under the same umbrella. So this is a recipe for building learning algorithms. Okay? So it's an important idea that you need to internalize, the idea of minimizing loss and what it really means. So let me move on very quickly to this idea called model selection. Model selection very broadly is how do you find the best model? The best model for a given data set depends on a whole bunch of things. It depends on what features you use. It depends on what hyperparameters. It depends on what laws you use. And it depends on which parameters, like the weights or whatever, that define the model. Notice that so far, all the learning algorithms that we've been looking at only talk about the last point. They only talk about how to find best weight given a feature set, given a loss function, given a particular set of hyperparameters. But if I actually want to use machine learning in an application, you need to decide on all those other things. And model selection is a family of methods, comprises of a family of methods that give you hints as to how to pick the best, all the other things. And you already know an answer to that. How do you do that? How do you find the best hyperparameters? Cross-validation. Cross-validation is a model selection strategy. I'm not going to cover all of these things because it's frankly one of those things that you can pick up by reading. And there are many approaches out there. The book Elements of Statistical Learning Theory gives you a good overview of this, and this book is available online. It's linked to on the class lecture. I encourage you to read this because it will kind of give you ideas on how to be a good machine learning practitioner. There are many ways of doing model selection, minimum description length. You can think of VC dimension as a way of kind of guiding model selection because it tells you that smaller VC dimension is preferred. There are other things. We've already seen cross-validation, and you guys are experts in cross-validation, so I'm not going to spend too much time on. The general idea is you need to know what's the best feature set and the best set of parameters given a training set. Just in pictures. Suppose you pick k-fold cross-validation. K can be from 5, 10, 15, whatever. Is the following process. You split the data into k parts. They are also called k-folds. These are equal sized parts that are chosen randomly. You train a classifier on k-1 part, on 4 parts, and evaluate it on the 5th one. And you do this for and you can evaluate using whatever metric is important to you. You can evaluate it using accuracy, or in your current homework, you're using the F measure. So here in your homework, you will be using F measure, the F score. And you'll do this for all possible choices of this evaluation set, the so-called test set within this setup. So you get 5 different accuracies or 5 different F1s. This is for a particular feature set and a particular hyperparameter setting. You've got 5 accuracies. You take the average of these, and the performance of this feature set and hyperparameter setting is this average. This is k-fold, 5-fold cross-validation. And you try that for all possible feature sets that you want to try. You try it for all possible hyperparameters that you want to try, and you get a list of different values of this performance here. And you rank them according to this performance, and the one that gives you the highest quality here is the one that you are going to sell, is the one that you believe is the best one in general. And you train your classifier on the entire training set using the best hyperparameters. Yes?
Should we shuffle the data before we split?
Yes. You need to shuffle your data before you split, but one thing that I have seen people do, and it's not entirely wrong, is you decide on the splits up front. So that all your every experiment, this is going to be repeated for every possible hyperparameter. All of them are done on the same splits, and also so that you can kind of compare them and do do error analysis. One way of doing error analysis is to analyze all the predictions in these 5 things, and if you have the same splits, you can do the error analysis easily. Yes.
I was going to say, something I did notice with like some of the competitor project, and something I noticed in this tips is like you gotta make sure to shuffle your data. Actually, even just like when you pull in the data, it seems like that's necessary. Otherwise, cross-validation may not give you accurate results.
Yeah.
Because it was ended up like it was off by like a factor of 10. It's like the cross-validation results versus the actual, or like even
Factor of 10.
Yeah, it was really weird, but that was the issue. Like when I shuffled it, that it before just initially when I read any data, then it aligned again.
Okay, in general, shuffling fixes a lot of problems.
Yeah.
When you're sampling though, when you're splitting, sometimes you have to split so that each split is representative of the true data. So if your data has 60, or let's say your data has 80 positives and 20 negatives. When you split, you need to split so that every fold has 80% positive and 20% negative, so that within the folds are representative of the entire training set. There was a question?
If you're seeding your solver with random variables, do you need to keep the the same set of random
I
variables
tend to.
start with
I
for
tend to.
cross-validation?
I tend to do that mostly so that if I run the same experiment again, I get the same numbers. And it's practically that is a good thing to do. Okay, so I feel like you guys are experts on cross-validation at this point. You've been doing this since homework 1. I thought this would be a good opportunity to put it in the perspective of model selection. And you repeat this for every hyperparameter and blah blah blah. The general strategy is you evaluate every possible feature and hyperparameter setting using this process and pick the one that's the best, which is obviously going to be computationally painful and also trivially parallelizable. So if you, I know some of you are experts on distributed systems and MapReduce and things like that, you can, every cross-validation fold can be sent into a different computer, for example, because there's nothing in common. So you can, the cross-validation is one of those things that's trivially parallelizable. If you like GPUs, you can do cross-validation on GPUs because there are so many cores. Did you have a question?
No, sorry.
Alright, so that's pretty much all I'm going to say about model selection. Model selection is a massive area of a lot of practically useful things. So I encourage you to read the resource, the chapter 7 on, I think it was chapter 7 in one of the editions. You will find, if the editions have changed, you can always, you know how to find it. But the book is Elements of Statistical Learning Theory.
Is that the ebook?
Yes, yes, it's the book that you can find online. Alright, the final thing with about the 6 minutes that are left, or 7 actually, that are left, I'm going to try to introduce you to this idea of bias and variance. Every learning algorithm makes assumptions. You always make an assumption. In the form of this hypothesis space. If you are running a perceptron, you've already assumed that the linear classifier is the one that you want. Or you can pick a decision tree. You can pick a decision tree with depth 8. Or you can say that I want a quadratic transformation. So you're making all these assumptions. Now, you need to, while making these assumptions, it's possible that you are restricting yourself to a hypothesis space which does not contain the true classifier, that agnostic setting. It's always going to happen. But you can always ask, what is the error of the best possible classifier of my hypothesis space? If the error of the best possible classifier in your hypothesis space is lousy, then the hypothesis space is not a good choice. This performance or the error of the best classifier in your hypothesis space is called the bias. So if the true function is not contained in the target, if the true function is not contained in the hypothesis space that you're searching, it's possible that the bias can be pretty high. It will definitely not be 0 because the true function is not in the hypothesis space. This idea where the bias is high is called underfitting. You're using a hypothesis space which does not have the capacity to represent the true function. That is called underfitting. The bias is high. Okay, this is called the bias of the classifier. Notice there are two different things that means that, the word bias means two different things in machine learning. There is the bias feature, which has nothing to do with this, and there is the bias of a hypothesis space. The bias of the hypothesis space is the true error or the loss of the best possible classifier. There is a completely different thing called variance. Variance is how much does your learning algorithm depend on the choice of the training set that you have. You have only one training set. It's possible that if you just change the training set, your training set is randomly sampled, right? If you just get a different random sample of the training set, your performance might wildly vary. If that happens, you say that the variance is high. So if the best classifier is extremely strongly dependent on the training set, meaning you're overfitting the training set, then you say that the variance is high. So, in some sense, we want the variance to be low because you don't want the hypothesis to be very strongly dependent on certain perturbations to the training set because that means you're overfitting. Does it make sense intuitively? Does the word make sense? We've already seen this concept. I want you to, this is a terminology that is often thrown around. Bias means how much do you lose by committing to a particular hypothesis space? Because you might end up not having the capacity to represent a true function. Variance is how much will the performance of the classifier, the true performance, or actually accuracy of a classifier change because the training set that you have is idiosyncratic. So ideally you want to reduce bias and variance because you don't want to have a bias. The best situation is zero bias and zero variance. Never going to happen. Variance tends to increase if you get more and more complex classifiers. Extremely high variance classifier, an example of extremely high variance classifier is literally remembering the entire training set. I have a training set, I remember all possible examples in the entire training set, and I return the label of the examples from the training set. It's going to have terrible variance because if I change the training set, the classifier changes. And typically, variance decreases if your training sets get larger and larger because it becomes less sensitive to actual subtle variation. Any single example is going to affect it less. One way of visualizing this bias and variance is by thinking of this game of darts. Suppose the true concept we want to learn is the center of these dartboards, and every dart is a different training set. The best situation that we want is in the middle. It depends, irrespective of whether how much you change the training set, you end up at the center of the dartboard. Not very far. It's like the classifiers that are produced are close to the true concept. High bias and low variance is a setting when the variance is low. They are all clustered tightly, but the center of this cluster is far away from where we want to be. So there's this big error because our search space, we are not even targeting the center. That's high bias and low variance. High bias and high variance is the darts are all spread out. We are not even targeting the center, and every throw that we get is kind of spread out. Every data set is not representative. And of course, there's low bias and high variance, which is we're generally going towards the center. This is we're generally going towards the center, but not this like we're spread out quite a bit. So if you want to know how I play darts, I'm here. All right. So does this intuition make sense? Okay. And many times model selection or regularization and all these other things that we do can be seen as a trade-off between bias and variance. So there are three things actually that contribute to errors: bias, variance, and actual noise. There's nothing we can do about noise. We can try to control bias and variance. Higher bias means both the training and test error will be high. High variance means it's possible that the training error is low, but the generalization error can be pretty high because we are overfitting the training set. And this idea of studying bias and variance trade-offs has been quite extensively studied in the world of regression. There's some work in classification also, but in regression, you can actually formalize this quite nicely and you lead to very beautiful, it leads to pretty beautiful math. In the minute that I'm going to take over the class time, I'm sorry, I want to quickly run through this list of how do you control bias and variance. Ensemble methods reduce variance. If you have multiple classifiers that you combine, they tend to reduce variance. We've not seen k nearest neighbors, but as k increases, bias increases and variance reduces. We'll get to that later. Decision trees of a particular depth, if you have depth restricted decision trees, increasing the depth reduces bias. Why? Because as you increase the depth, you can fit more and more data, right? More and more, the classifiers get more and more expressive. Higher bias can be seen as a way of is another way of thinking about how expressive is your hypothesis space. So increasing the depth of the decision tree leads to lower bias but higher variance. Why higher variance? Because more depth can overfit the training set. SVMs, more complex kernels leads to lower bias but higher variance. Why? Because it can overfit training sets. If you have strong regularization, it increases bias because you are actually restricting the capacity of your classifiers. You are increasing bias, but it turns out it also can decrease variance. So that's why regularization is important. So let me just wrap up. We saw 2 or 3 really big ideas in this class, in this section. The idea of learning as loss minimization, an extremely important idea that you should you should go back and try to understand this more carefully. I briefly touched upon this question of model selection, and cross-validation is an example of this. And sometimes you will see, if you're reading papers and the books, you might see this discussion about bias and variance, and I try to put this in the context of what we already know in terms of overfitting and underfitting. Alright, let's stop now, and just remember that there's some homework, so please get done with it.